Okay, this is a good question to start with. It's an LCR circuit. You can see we've got an inductor, a capacitor, and a resistor. Let's just remind ourselves of some of the relevant equations to this. Voltage maximum is equal to √2 times RMS voltage. Capacitive reactance measured in ohms. This is the capacitive resistance, as it were, of a capacitor, 1 over 2 pi fc. So note, as the frequency increases, the capacitive reactance decreases. So that's like as the frequency increases, the resistance of the capacitor reduces, which is what you'd expect, because if the frequency is quite high, then there's not time to fill the capacitor up, so before it discharges with the alternating current. So we'd expect to have less resistive effect, so the capacitive reactance is inversely proportional to the frequency, whereas the inductive capacitance XL is equal to 2 pi FL. So that means as the frequency increases, the inductive reactance increases, which again is what we'd expect, that as the frequency increases, the change in current, the change of flux increases, so we'd expect greater resistance there. And the last couple of things to look at is, here is our phasor diagrams where we can see that the voltage in the inductor leads the voltage in the resistor by 90 degrees pi upon 2, and the voltage across the capacitor lags behind the voltage in the resistor by 90 degrees. And remember that the voltage across the resistor is in phase with the current. So let's have a look at that in terms of the sine waves. We've got the black line here. The black line is the voltage across the resistor, and again in phase with the current. And we've got the red line, the voltage through the inductor, and you can see that leads the voltage through the resistor by 90 degrees. So the voltage through the inductor leads the current by 90 degrees as well. And the green again, that's the voltage across the capacitor. So again, if we look back at this diagram here, we see that the current and the voltage through the resistor are in phase. The voltage across the inductor is 90 degrees ahead. The voltage through the capacitor is 90 degrees behind the voltage in the resistor. And then the last bit, which we'll come across it in the last part of the question, is for resonance, the inductive capacitance has got to equal the reactance. Then inductive reactance has got to equal the capacitive reactance. So we'll have 2 pi FL equals 1 over 2 pi FC. So we end up with this formula here, where we have the resonant frequency equal to 1 over 2 pi square root L over C. So we'll need that for a little while. So let's go back to our questions. And we've got our first question: calculate the peak voltage of the supply. And we've got that the maximum voltage, the peak voltage, is equal to square root 2 times the RMS voltage. So that's equal to 1.414 times 65 volts. So that should give us 91.9 volt. And again, three significant figures, three significant figures in the answer. Okay, part B. The supply voltage of the circuit above leads the circuit current by 35 degrees. So let's have a look at our phasor diagram. That's this one here. The voltage across the inductor is always 90 degrees ahead of the voltage across the resistor. which again is 90 degrees ahead of the voltage across the capacitor. So we can draw our phasor diagram over here, and we'll draw it like this. We'll have the voltage across the inductor is up here, so this is also the inductive reactance, and down here we've got the capacitive reactance, and across here we've got the resistance. So there's our phasor diagram, and we're given that the resistance is 1.5 times 10 squared ohm, so that's 150 ohm, 150 ohm, and we're told that the supply voltage leads the current by 35 degrees. So let's draw our diagram in here of 35 degrees. 35 degrees. And we need to find the total impedance of the circuit. So this phasor here, this one here, is the total impedance. And from that diagram, we can say that cosine 35 degrees is equal to 150 divided by the total impedance Z divided by Z. Therefore, the total impedance Z is equal to 150 divided by cos 35, which is equal to 183 ohm. And again, three significant figures. Okay, part C. The inductor has an inductance of 0.380 Henry. By calculating the total reactance of the circuit, determine the capacitance of the capacitor. So this is a several stage problem. Let's start with the inductor has an inductance of 0.380 Henry. So we need to find the inductive reactance, and that we get from 2 pi FL. 2 pi, the frequency we're told is 50 Hertz, and the inductance is 0.380 Henry. So that means the inductive reactance is equal to 119 ohm. Remember, they're all in ohms, so that gives us that. So when we look at this diagram here, this distance here is equal to XL minus XC. And from our triangle, we can write sine of 35 is equal to XL minus XC divided by 183 from our triangle here. In which case, therefore, since XL, we worked out XL already to be 180. What did we work it out to be? We worked out XL to be 119 ohm. We can solve this equation for XC is equal to 0.000227, which equals 2.27. Bit of a slip up there. XC is equal to the reactance, the capacitive reactance is equal to 14 ohm, and then we can use our equation. XC is equal to 1 over 2 pi FC. Substituting in all our values, it'll give us the capacitance is equal to 0.000227 farad, and let's write this in standard form. 1, 2, 3, 4. 2.27 times 10 to the negative 4 farad. That's our capacitance. Those are the steps for that. Which brings us to question 4. Explain the change that needs to be made to the frequency to the signal generator to bring the circuit to resonance. Okay, let's come back to this then. For resonance, remember, for resonance, we need the inductive capacitance to equal the capacitive reactance, in which case 2 pi FL needs to equal 1 over 2 pi FC. So this combining them gives us a formula for the resonance frequency, which we'll use in a moment. But in order to get resonance, what we need is that the XL and the XC have to become equal. So we can see with XL, we need to lower this reactance, and with the XC we need to increase it. So how do we decrease inductive reactance? We need to decrease this. So in order to decrease that when inductance is constant, we need to reduce the frequency. So if we reduce the frequency, the inductive reactance will decrease. Similarly, if we decrease the frequency, the capacitive reactance will increase. So if we decrease the frequency, the inductive reactance will come down and capacitive reactance will go up. So that's the way we can do that. And we can then also use our formula to calculate what the frequency will be, what we need to change it to from the 50 Hertz. And we can see, if we solve that, substitute in all the values, we'll end up with 17.1 Hertz. So 17.1 Hertz is the resonant frequency, so we can see if we reduce it from 50 down to 17.1, then we will see that the capacitive reactance and the inductive reactance are the same, and we have resonance.